Welcome to my class. I am Mr. Dana Doherty. I am a science teacher here. This year I'm teaching physics and Chem 2. That's pretty much every year that I teach that. This year I'm also teaching robotics, so I also dabble in engineering. And this year I'm also teaching physical science, which I have not done in several years, but am well equipped to teach and very excited to teach it as well. A little bit about me. I got my bachelor's degree at Bethel College in North Newton in chemistry. At that point I decided that, you know what, I'm going to be a doctoral chemistry student, I'm going to be a researcher. So I went to the University of Kansas to get my doctoral degree in chemistry. Along the way I taught in a lab, there, an organic chemistry lab, and I loved teaching. And so I called up my old chemistry teacher at Iola, Mr. Marvin Smith, and I said, hey Marv, what do you think I should do? And he basically told me, you need to get down here and take over for me. So I was like, well, okay. So then I switched over to education, got my master's degree in curriculum and instruction, and here I am. This is my 9th year teaching. I'm very excited to be here and very excited to dabble in this new kind of learning environment and learning situation. So I wanted to give you a brief introduction to my classroom, to myself, but also to my classroom as well. Not so much like layout and stuff like that, which I'll show you some pictures of, but mainly for the fact of getting to know me and my instructional practices, because my instructional practices are a little bit different than probably what most people are used to. So I wanted to make sure that I've done that. First off, I teach what's called using modeling instruction, and so the question is, what is modeling instruction? To put it simply, I've basically identified the 3 steps of modeling instruction, which is used throughout every course that I teach. Robotics and engineering is a little bit different, but I use the same type of approach in engineering as well. It's very student-centered. I don't stand up here and lecture like what I'm doing right here very often. Usually the information is built by the students themselves. What I call modeling instruction is an empowerment to students, because what I teach them to do is to create models for themselves. So the knowledge that they learn in my classroom, they have the skills to be able to do science on their own. It's not a set of facts that they learn, it's a process in which they learn. So let's talk about modeling instruction real quick. The first step is called modeling development. So basically what we do is we develop this model. And what I like to call a model is just a way of thinking about a scenario. And I'll give you an example here in just a minute. So what are all the different ways that we can think about this particular scenario? And so we're going to develop this model by looking at some kind of scenario. And we're going to define that scenario and analyze it as much as we possibly can. And then from that, we're going to create or construct a model to describe that situation. Then what we do is we evaluate that model. In other words, we say, okay, what all situations does this actually apply to? And so we start looking. Does it apply to this situation? Yes, let's test it here. Yes, let's test it here. Yes, let's test it here. No, that does not apply. That's something we should develop another model for later. And then at the end of each modeling cycle, we do a modeling deployment. In other words, we look at some very complex scenario, and we basically apply all of the knowledge that we've done to solve some kind of applicable situation. So I'm going to give you an example of this real quick, of the modeling cycle. I'm just going to show this in the background. I'm going to slide this guy over here real quick. So here we have a pendulum, okay? And this is a lab that we typically do in physics. And so this guy is called a pendulum bob. And a pendulum goes back and forth like so. So typically what I'll do in my class is we'll look at some scenario like this, and we'll say, okay, I'll pull it back, I'll let it go. What observations do you have? And so kids will then be allowed to make any observation that they have. They could be as simple as it's hanging by a string, or it could be pretty complex, like, oh, it seems to be maybe following the same path. It seems to be that the time in between each one seems to be the same. Or it could be something like, gradually it's getting a little less higher, gradually, but not, if you look at each one, it's pretty much the same. So observations like that. And then what I do is I use those observations to say, okay, what observations can we actually measure? And somebody will be like, well, we could maybe measure the time that it takes to go over and back. I'd say, well, that's called a period. Good answer, that's called a period. Let's write that down as a term that we should know. So the time to go back and forth, called a period. And then we could say, okay, what kind of things would impact the amount of time that it would take to go back and forth? And kids can come up with a whole bunch of different things. And so somebody might say, the distance that it's pulled back. So if I pull it back this far as opposed to this far, is it going to take longer? We can do an experiment to test that. What about the height above the ground? We could test that. What about the length of the string? So if I went up like this and made it shorter, how is that going to impact the time? And so what we do is we come up with a whole bunch of things that could impact the time that it takes to go over and back. And then we create several experiments. Students conduct these experiments, and what they do is they create a graphical model of that. And so I'm not going to plot what those graphs look like because I don't want to give away answers because this is a lab that we do. And so we get graph shapes, and from those graph shapes, it tells us a story. It's helping us develop this model of a pendulum motion. Then what we do is we come up with some kind of pictorial representation to explain it. Like, for instance, this is a force diagram. I can say if the force of tension is pulling it. If I pull it back here, the force of tension is pulling it this way. We have force of gravity pulling it down. We also have things like energy bar charts, which we can use to explain it. So we try to explain the scenario from several different pictorial representations as well. And then finally, we also use mathematics. And so we generate equations. And I will say this, I wrote the standard equation for a pendulum motion. However, we don't actually write that equation in class. What we do is we generate the equation from the graphs using our slope-intercept form that we learned in math class. And so we take some kind of equation, we find a line that would fit it, then we run a linear fit through it, and we would physically come up with that mathematical relationship ourselves. After we got done with all that, then what we could do is we could test it to see all these different scenarios, and then on the deployment I could say, okay, well, what would the period be in this kind of scenario if I pulled it back this far and had it this short? And they'd have to predict, and we could test. And that would be the modeling cycle. We do that pretty much within every unit, and sometimes within unit we do that several times within each unit as well. The key thing is modeling development focuses on student being forced to think for themselves, because I'm not in the business of telling students a whole bunch of facts. I'm in the job. My job as a teacher, I believe, is to empower students to create that knowledge themselves. So that is modeling instruction, and that is what your students will be doing in my class this year.